Welcome friends to my YouTube channel Shommo Physics. In my previous lecture I told about Carnot theorem, the first part of Carnot theorem, that is efficiency of all reversible heat engines working between same two temperature limits are same. Now I shall discuss about the second part of Carnot theorem, which is nothing but no engine is more efficient than a reversible engine. No engine is more efficient than a reversible engine. So how we can verify it? Okay, so we consider two engines working between same two temperature limits. This is source and this is sink. We consider two engines A and B, say. Okay, suppose the engine A absorbs Q1 heat from source and rejects Q2 heat to sink. This is at temperature T1 and this is at temperature T2. And the engine B absorbs Q2 dash heat from sink and rejects Q1 dash heat to source. Obviously external energy is supplied in this case, otherwise this is not possible. So the engine B acts as a refrigerator. Okay, engine B acts as a refrigerator. Engine B acts as a refrigerator. Okay, now let us assume that B is reversible and A is more efficient than B. Okay, assume B is reversible and A is more efficient than B. Okay, so assume B is reversible and A is more efficient than B. That means we consider B is reversible and A is more efficient than B. So we have to prove this statement wrong. We have to prove that this statement is wrong. Okay, because our main aim is to prove no engine is more efficient than a reversible engine. But here we consider the falsity. We assume B is reversible and A is more efficient than B. So we have to prove that this assumption is wrong. So how we can prove it? Let's proceed. Okay. Now, so we assume that engine A is more efficient than engine B. So eta A obviously greater than eta B, that we assume. Now what will be the efficiency of engine A? 1 minus Q2 by Q1 here. 1 minus Q2 by Q1. This simply equals to 1 minus Q2 dash by Q1 dash. Okay. Now simply Q1 minus Q2 by Q1 greater than Q1 dash minus Q2 dash by Q1 dash. Now we have to consider the second assumption. What? Our second assumption is that the engines are so coupled that work done during each cycle for the two engines are same. Okay, this is also another assumption we have to consider. A and B are so coupled that work done during each cycle for both engines are same. So if this is the second assumption, then we can clearly write W this equals to Q1 minus Q2. So this equals to Q1 dash minus Q2 dash. So if we substitute this assumption in this, so what we get? 1 by Q1 is greater than 1 by Q1 dash. That means Q1 dash is greater than Q1. So if Q1 dash is greater than Q1, then similarly from this expression, what we can write? We can write Q2 dash is greater than Q2. Okay, so it is clear that Q1 dash is greater than Q1 and Q2 dash is greater than Q2. So what happens? So what happens in this case if that result is found? That means actually Q1 dash greater than Q1 and Q2 dash is greater than Q2. So what happens? This means in each cycle Q1 dash minus Q1 equals to Q2 dash minus Q2. In each cycle, this amount of heat is transferred from sink to source. Okay, so in each cycle, this amount of heat, which must be equal to this, that is Q2 dash minus Q2, this net amount of heat is transferred from sink to source. Okay, so in each cycle this amount of heat is transferred from sink to source. Okay, but here in this case there is no external agency, so heat cannot flow from cold to hot body. Okay, from our calculation we have shown that during each cycle this amount of heat is transferred from cold body to hot body. Okay, but in actually what happens? In this case there is no external agency, that means heat will not flow from cold to hot body. So what we conclude? We conclude that our assumption was wrong. What we assume is totally wrong. That means the engine A cannot be more efficient than B, which is a reversible engine. Okay, so in each cycle Q2 dash minus Q2 heat is transferred from cold to hot body. In each cycle, this amount of heat is transferred from cold to hot body. But since there is no external agency, heat cannot flow. Heat cannot flow from cold to hot body. So our assumption is wrong. This means what? We assume that B is reversible and A is more efficient than B. So that's not possible. That means eta A will not be greater than eta B. Okay, which is reversible. The maximum possibility is that both the engines have same efficiency. Okay, so this proves the second part. No engine is more efficient than a reversible engine. Okay, so this is the second part of Carnot theorem. Okay, so I hope all of you understand this. Okay, this proof is necessary for both graduation students and also CBSE ICSE students. Okay, now what happens? Now we shall discuss about few other things related to entropy. First of all, I shall discuss today, the factors affecting entropy. The factors affecting the entropy. Okay, so what we discuss at first, we shall discuss the factors affecting entropy. Okay, now what is the first factor? The first factor is that state of a substance. Okay, the state of substance. Let's check how it affects the entropy. Okay, now we all know that the molecules of a solid are arranged in regular and periodic manner. Okay, molecules of a solid are arranged in regular and periodic manner, and they are packed densely. Okay, they are densely packed. Okay, the molecules of a solid are arranged in regular manner, ordered manner. That means solid substance, solid has less entropy. Solid has less entropy. Okay, why this is? Because the molecules of solids are arranged in regular and periodic manner, ordered manner, so it has less entropy. Now if you look back the molecules of a liquid, then they are not arranged in regular and systematic manner. They are arranged in non-regular manner, or you can say the molecules of liquid are not arranged in regular manner. Okay, so in this case the disorder is greater, so liquid has greater entropy. So this is the first. Okay, the type of substance, if you consider the solid, then its molecules are arranged in regular manner or ordered manner, so it has less entropy. But the molecules of liquid are not arranged in regular manner, that means there is a disorder, so liquid has greater entropy. So this is the first, that is the state of substance. Okay, now the second thing that can affect the entropy is the number of particles. Okay, what happened? If the number of particles increases, what happens? We all know that if the number of particles increases, then the chaosness or disorder increases, so entropy increases. Okay, suppose there are 5 particles in a system, and if suppose now the particle number is raised from 5 to say 25, then obviously the chaosness or disorder increases, so entropy increases. Okay, so entropy increases with increase in particle number density. Particle number density. Okay, so this is the second thing. Now another thing, how temperature can affect the entropy. Let's check. The third thing is that how temperature affect the entropy. We all know that when temperature increases, the vibration of the atoms or molecules becomes large. Okay, so if vibration is large, that means chaosness is large, disorder is large, so entropy increases. Okay, so if we rise the temperature, okay, if we rise the temperature, then the vibration of the atoms or molecules becomes greater. So if vibration becomes greater, then the chaosness becomes greater and the entropy is larger. Okay, so due to rise in temperature, due to rise in temperature, thermal vibration, that is chaosness increases. Chaosness increases, hence entropy increases. Okay, so thus we see that with rise in temperature, thermal vibration increases, as a result chaosness increases, and entropy of the system increases. So this is how these three factors can affect the entropy. At first we discuss about the state of substance. Okay, now then we discuss about the number of particles, and then we discuss about temperature. Okay, so this is what about today. Now in our next class we shall discuss about the temperature entropy diagram. Okay, so dear guys, if you don't subscribe my channel, then kindly subscribe it and share it to your friends to get latest updated videos. Okay, thank you.